Okay, welcome back. We will see how we can create intelligence by creating adaptive behaviors, and we will look how that works both in nature and in robots. So, first we will try to teach you why we should have adaptive behaviors, why the system should learn, and what to learn and how to learn. And we will dive into that. So, learning, what's it? Learning produces changes in the behavior of the agent over time, and the main advantage, both in the animal kingdom and the robotic kingdom, is that they perform their behaviors more effectively within their environment. So it's learning from experience. And adaptation is purely to apply the learning of the agent to make adjustments in the settings, the parameters, and of the behaviors to get more and more attuned to the environment. So that can be partly done experimental by the researcher or by the system itself. So what can you adapt? So partly you can do it by adjusting which behavior gets active. So then you change the selection scheme. What you also can do is that each behavior itself learns from a previous experience, the schema-based approach, where the previous instantiations are used to get a better response this time. You can learn to perceive better when you know that the grass is green and the road is dark. Then you can attune more and more to the environment. The downside is that you can be too much attuned to an environment, but it's also stupid not to learn that in most cases grass is green. And you can also see the learning behavior as adaptation. So that's everything else that makes sure that the agent survives. And we will see some examples of the genetic approach later on. So adaptive control is already something that is quite old from the cybernetics. Partly that was before the Second World War. A lot of the control could be done, manually. But they found out that some processes went that fast with the coming of the rockets and the fighters, that you need more and more to have adaptive control loops. And in the cybernetics, there was a lot about closing the loop with conventional feedback, but also to put a learning element into it so that you can adjust your feedback loop to get more and more with it better controllers. So, what can you learn? You can first learn better world models. So new facts, new behaviors, new rules, and that's great. And for sure, if you can make your behavioral set larger and invent new behaviors, that's the thing that we want. What you also can learn is that something that was in principle working in a specialized setting, that in principle it's a concept that also works in a broader setting, and then you learn to generalize concepts to everywhere. If you learn to cook, you can also do some chemistry, or that's part of the recipes you can use, and that's say transfer learning. What you can also learn is the other way around, is that you learn more specialization, so that you adapt your behaviors for specific circumstances. If you can drive in the traffic, you can specialize on driving fast on your bike or driving fast on your car. What you can also do is you get a lot of information, and that works fine for in the previous situation, and you can keeping adding information to it, but at a certain moment it's good to restructure it because that works better for these circumstances, and it means that you have to redo the structuring of your world model, and in principle the same information stays there, but it's ordered in a different way. For sure, with the internet, say you can get a lot of new information from everywhere. Part of it is new concepts that you can include in your behaviors. For sure, if you think about a kitchen robot, there are always new recipes and new ingredients that you can start working with and learn to get a better cook. Another thing, and that's one of the hot topics in artificial intelligence at the moment, is that not only that you learn what to do, but that you also learn why you do it. So you give better explanation why this is a good choice. So adding sort of reading guides why you're doing it. So that's great, because the robots have to function in a human environment. So how better they can explain what and why they are performing like they do, that will increase the trust. And last but not least is learning is making a lot of use of what you have encountered before. So it's a waste of time if you don't reuse all your past experiences. So learning is something that comes forward in artificial intelligence. So you have many types of learning. For robotics, what really is special is that a lot of the learning is done by reinforcement learning. That means that you don't have examples what to do, but the only thing that you can do is let the robot actually manipulate the environment, do something, and then look back if that was a good choice or not. So what we'll see is that the most important here is what sort of signal you give back to reinforce the robot, if it was good or if it was bad. A lot of the current training is done by neural networks. Well, what's currently really popular is the deep learning with the networks, and we'll see some examples from that. What is also with it a way of learning is if you have a sort of a genome, and that you starting to play with the rules by encoding the rules in genome, and get more and more with it better rules. That's really a great way by mutation to come up with new behaviors. So you can learn with it from experience. Part can be memory-based, where you learn with it more about the world, but it can also be that you learn with it for a specific behavior, and that you learn to apply one action better and better before. One with it, other with the dimension you could go is in inductive learning. That's with it playing some of the scenarios through simulation to see what the effect could be. and another way is that you ask for the users for explanations, and that you get clues where to go there. And last but not least, you can try that all together with multiple strategies and with multiple objectives. Okay, where in the behavior-based approach you could learn, that is on two different parts. One is that you can make better and better behaviors, so you train inside the behavior. What you can also learn is better combinations of behaviors, so that you learn when to apply a behavior, or the relative strengths between different behaviors, or to better recognize the conditions where you should apply your behavior. That sounds great. Is it easy? No. Partly, if you, and for sure in behavior-based robotics, if you have multiple behaviors active, and if you're playing soccer, for instance, you score a goal, who to give all the credits? The one that scored the goal, of the one that gave the assist? In often the emergent behavior is the combination of a lot of the combination of the different active behaviors. So it's very difficult to distribute in a fair way that credit over the whole part. Also, you have the saliency that is maybe a decision far in the past was the thing that makes sure that you scored now. So you have also to think about the credit assignment over time. Other problems is to think about how long you continue working with improving an existing behavior, or when to start a new behavior, a new term to get it. And then what you also have on the last part, the utility. So what is a good utility? So a scoring function for one behavior doesn't have to be a good utility for another behavior. So will you make a separate utility for each behavior, or will you have a joint utility? And then you have again how do you distribute it over the different behaviors. So reinforcement learning is really an old concept. It was already formulated by Thorndike in 1911. And what you will see is that if you have a response that is good, then you can give a reward directly afterwards, and that will help to increase the probability that such a response would occur. And if you give a punishment, then the probability should decrease. So what you need is not only a feedback loop, but also a critic. And a critic says if you're doing well or doing not well. And that sounds maybe more difficult, even more difficult than creating a good feedback loop. But in a way, it's sometimes more simple. One example I always use is in 1911, you still had a lot of, say, doctors in the village, well-educated men that went through the whole village to help to cure the sick. but you didn't have any mobile telephones there. So an important role that was playing was his wife, and probably as intelligent, but she was not allowed to study any medicine at that age. But still, everybody that needed the doctor came to her, and in a state of panic, and they told the story, and she was then the one that has to do the triage if it was really needed to get her husband from one of the farms far away, because this was really an incident, or just give a cup of tea and reduce the panic and say he will come up later that afternoon. And that's partly also how we built our current system with first and second rate responders, where you try to put that in. So in that sense, the critic, if is seeing if something is really wrong, or if something that's mendable, that's quite easy. So reinforcement you can do in two different ways. In both cases, you get a lot of information about the state. What you can learn is that you build a critic that says how well this state is, and if you should go away from that state, or that is the beneficial state. And at the same time, you can learn policies based on that utility to select the actions that higher the utility you will get in the future. But that's often quite difficult because the state is not the only thing that's informative about how good it is. It's often the combination of a certain action in a certain state. And it's often more easy to learn the combination. That's called the Q function. What sort of reward you could expect if you apply a certain action in a certain state, and that's Q learning. So that's applied with it quite often. One of the first places where that's learned was by Brooks. Brooks was the one from the subscription architecture, and the one that said that the world is the best model you could get. And he learned Genghis. That's a sort of caterpillar, a sort of a robot to walk and to be stable, and that was learned by Q learning. And this is a small video of the first steps of Genghis, and you see that each of the legs was learned how to walk. And you saw that if you give as enforcement how much progress you make, that it learns the gates that you also can see in nature. And the nice thing, if you learn that in an a hostile environment, it can also learn how to get up to a number of stacks of Python books. Okay, so Genghis was not the only one that applied Q learning. Also, Obelix was one of the robots that used Q learning. The colony architecture was an example where already Q learning was applied. And what they learned was how to push together against a box, and learning it's with Q learning. You see that you get far better performance than do it hand-tuned. We had some examples of the IBO with it, robots that used learning techniques to walk faster. And if you let them walk for 1 week in your lab, then you could see that you could outperform hand-tuned controllers with 20-30% faster than you can design yourself. So Obelix with it learned to perform better. So we will look into that. What they did is that they made a stacked hierarchical approach of different subsumption layer. On the lowest layer there was a finder that was looking for the boxes to be pushed. Then you had the pusher that took over the control and pushed it to the place where you want to be, and where it was to be, then with it you disconnected again. So what they did, they used Hebbian learning that all the connections in the network, the perceptron, was strengthened based on the response that you get, and by backpropagation you could go from if you see the difference between the response that you expect and the response that you actually get, the difference can be backpropagated through the network, and that's still used in all current networks. The big difference that in that time they used perceptrons, so that were typically with the networks with only one hidden layer. So that's partly also what you have learned from psychology. There also you have a classical condition. So what you learn is that if you show a certain behavior under a certain condition, and you learn also to apply a second behavior, if then the first stimulus is not longer there, then you still show that same behavior. And that was work that was actually performed here at the University of Amsterdam, and they learned to get the association between different stimuli, comparable with the Pavlov reaction that a dog learned to start already have salvation if it only ring a bell. Other approaches with the advanced heuristic critic is that you learn different critics, that every one learned a different gain multiplier, and you could apply that to learn faster. That was shown on more advanced robots than Genghis. This is a whole program of Lauron in French, where they used that advanced critic method to learn the leg coordination, and they built a whole sequence of different robots for that. I will show you the difference in progress between the Lauron 4 and the Lauron 5, and you see already how stable this robot is compared to the Genghis robot. Its body stays most of the time flat, and in Lauron 5 you can even see that it can start to work over slopes. And you can slowly increase the slope every time. So another place where they used perceptron learning was Edinburgh. There they learned a robot to navigate based on its whisker and infrared sensors. In principle, there were only three actions to learn: go straight, or going left or right. And what they did was that the robot was taught how to behave, because the experimenter was giving more and more challenging with it environments. So the way to learn the robots what to do is by with it giving them the right challenges. So what you see is that on the top you have the sensors, the infrared sensors and the light detecting sensors. What they first do is a novelty detection. So for sure, if you have such a quite shallow networks, it's really important how you pre-process your data. So only if there's something new that was detected, then you create the input factor, and it was coupled to, in the end, the three different actions: going straight, going left, and right. And then with an arbiter, it was decided which of those three suggestions to follow. Okay, that's what some examples of neural network learning. Other ways of learning is by genetic algorithms. There, in principle, you put the rules that are active inside behaviors in a certain encoding. You can do that direct or indirect. Indirect is actually with it a little better. But once you have such a set of coding, then you can start working on modifying that code. One thing what you can do is reproduction. So you have two genetical codes, and you combine it to a new genetical codes, and then you have to select who's the fittest two parents. So you can think that of male and female, but in most cases is the two most fit species that you use. You can use the two genes as is, but you can also starting to move part of the genes from one parent to the other, or you can use just one of the gene code and start mutating part of the genes. So you can use algorithms like this to start with it working on it. And what you typically do is that you have a whole generation of species. You give them a gene encoding. You send them to the environment and see how well they do. And based on how well they do, you use that to generate a new generation of robot controllers. So how can you use such genetic algorithms that is demonstrated in Alexis, where they built an autonomous mouse. And in principle, you had typically direct coupling between the sensors and the actuators. You mouse get in a number of messages, and what was done is that it was classified what sort of situation it was, and based on that situation, a certain response was done. And what they did is that they learned both a critic and a genetic algorithm to get that classification better and better. So that's on the sensor part. There's also a lot done with genetic algorithms, not only on behaviors, but also on the shape of the robot, because body and behavior is done quite related to each other. And what they learned were sort of robots that could walk or swim quite fast. Now, here at the University of Amsterdam, we also worked with such an algorithm. This is a robot that learns to walk in different environments. The sort of environments that they differ. They're all it is flat, but in principle it are surfaces all over with it on different planets. So based on what sort of planets they are, what sort of shape and what sort of behavior they should show. You see here how that is used. You see here with it four with it colors. In principle, you have two sort of bones, with it, blue bones that are really fixed, and red ones that are a little bit soft. And you have the two sort of muscles, in dark green and light green. And based on that, you indicate where with it in this cube you should have which sort of bone, and you make a sort of skeletons and make different sort of behaviors. And what they did is that they started with an initial population. They sent it to one of the simulations with different gravity. There you see in the middle the big cloud with different size of the different species. The size indicates how well they performed. You sort that, and then with it you start combining based on the sorted list who with it could survive without any modification. That's the atheism with it part. The winner with it may always continue as is, and the one after it got or mutations or crossovers and were sent a new population, and that one is evaluated again. What's nice, if you do it like that, then you only look for fitness. Then you see that you get a very optimal, but all more or less the same solution. What they did is that they also looked on the entropy, so how diverse the population was, and also put a separate fitness function to that, and that's allowed also to breed based on diversity. And then you see that the solutions are far different. And the nice thing is that if you allow such diversity, that also the performance, the fitness with it increases more, because the ones that continue to optimize in the same direction never found the new innovative solutions, and they stay in a local minima. So by not only having a blue with it row, but also a red row for fitness, but also a blue row for novelty, you get a much better with it selection of your the next generation that you can train. So another with it part that's really important is this is training and every time breeding a new generation, new childs. What's specific to the humans is that we have a very long childhood, and if we learn a robot to walk, that's comparable with what you do as a child when you're 1 year old. So it's a bit strange that we expect that all our robots are as long and with it as capable as we are. So it's far more reasonable to make them the size and also the capabilities of a child and train them as a child does. So that is the project that was started here in the European Union. That's the ECAP project, where they trained the robots to recognize humans, recognize balls, and to learn to play with different objects. And you don't expect them to learn from scratch. Okay, the part that we haven't touched yet, but what was also really popular in the 90s and still is relevant in the pre-processing of the data that you send to the neural nets, is that in most cases you get a lot of signals that are floating point numbers, and the problem is that most of those numbers are not normalized against each other. So if you have a length and a weight, then there is a factor 50 at least difference between your length and your weight. So you have to scale that, and how do you scale that on a reasonable way? And what they did is that they did a lot of study about physicification, where you learn how to combine certain input variables that were continuous into sets, and the sets are in principle not have fixed boundaries, but have overlapping boundaries, and you get then concepts always thick or thin, long or short, and yeah, a lot of people are a little bit in between, and with fuzzy logic you can cope with that. So what you would do in the beginning is you physify all your input, and on the end you get steering results as going a little bit left, going a little bit right, and that's then dephysicified again to real numbers. So there's fuzzy rules you can specify, but you can also let the system learn that, and that's applied quite often. What the best membership are. What's an example of such physicification? That is an example of a steering wheel where they learn how to drive on a road, and it was nicely done with already in the 90s, where you see a sort of Back to the Future car with most of the equipment built on the trunk, and that they learned with it how to stay on lane. And don't forget, we are talking now a lot about self-driving cars, but already in Europe in the 90s we were able to demonstrate with Dielman to have a self-driving car on the peripherique of Paris. So those systems have already a very long history, and for sure on the highway with it, driving is not that difficult. It gets difficult if you go off the highway. So we have seen with it the most common types of learning. There are with it many other types of learning: case-based learning, memory-based learning, but we'll go not that much deeper in it. The only exception is case-based learning. That's highlighted in the book from Arkin, where they learn, if you have an example like this, where you have a local minimum and all your behaviors put you in the corner, that you then learn that you have a case that you're stuck and how to get out of that. And that's a nice thing, is learning what the situation is and how you should learn a new behavior to get out of that situation. So that's what I want to teach you today about adaptive behaviors. Adaptive behaviors are essential to learn the robots to adapt to a changing and dynamic environment, and that's precisely where they have to survive. Behavior-based robotics can learn in two ways, or they can learn to improve their behaviors, or they can learn to create new sets of behaviors. And part of the learning can be, as we've seen with the e-cup case, for one robot itself that learns to behave much better, but you can also give your experience to another generation and improve between generations. Okay, that's what I want to tell you about adaptive behaviors. Hope to see you next time.